Sure. Hi, everyone. I'm Ali Shojaie. I'm a professor in biostatistics, and I've been the lead of the DMS core for a few years now. And I'm taking over one of my other colleagues who retired a while ago, Ellen Wiseman. And so today, what we're planning to do is that my colleague at DMS core, Tang Le, who's here as well, and I will give you a brief overview of what the MS Core could do, in a sense. The idea is that we'll talk a little bit about sort of the resources that are available, different types of data that are available. Tong will show you a little bit how to interact with our resources in our databases. And then I'll tell you a little bit about sort of more didactic, but sort of a little bit about how to think about sort of analysis plan and sort of how to think about sort of getting to the point of analyzing your data once you obtain your data. So that's the plan for today. So Tom, maybe you could start, and then after a little bit about maybe perhaps 20 minutes or so, 15, 20 minutes, that Tom will give you some overview, then I'll talk a little bit about analysis.
Great, thanks, Ali. So I'm Tung, so I'm the informatics developer for the ADRC DMS core. So I'm going to talk about the central database. So this is the public-facing, I guess, sort of public, because that is really mainly for UW ADRC researcher, but it's the way for our researcher at UW to interface with the data that we collect in DMS. So briefly, this is basically the data warehouse, for the ADRC data, which primarily consists of UDS data, but we also have legacy samples and genetics data we store in the central database. So let me share a little slide. So this is what the kind of the overall architecture of the central database. So it consists of a relational database, which contains UDS data, data that can correspond to subjects that go through the ADRC. We have some neural path data that we collect. We have genomic data. We also keep samples. So these would be clinical biomarker, ApoE data, we have them, and where they're kept. And these are, also indicators too of other samples. In the future, we may host biomarker and imaging data. Some of the service that we provide outwardly to our web server are reports, dynamic reports. You can look up subjects, ADRC subjects through the web page. There's a query engine. We have user management. There's a data sync tool that moves data from the clinical core EDC into the central database. And we also host a few Shiny applications. These are core specific applications. The data that goes into the central base come from many different sources, but primarily we get them through the REDCap. There's one for the EDC. Obviously, those are the UDS data, as well as NeuroPath for IB core repository for the CSF data, and then some other data from the admin. Legacy-wise, a lot of the data comes from the previous clinical core, which is hosted at the VA, and we import that data for the access database into the central database and host that.
Tom, maybe if I could interject and ask a question briefly. So the assumption here is that sort of people are generally familiar with the division of labor within ADRC and sort of different cores within ADRC. Is that a fair assumption, or do we need to talk more about that?
I think it's maybe worth running through that real fast.
Okay. You want to do that, Ali?
No, I mean, go ahead.
Okay. So clinical core takes in data that ADRC subjects to go through the yearly visits, and they collect that data, and we upload it into a national art repository called NAC. And so we're sort of the data hosting of that. We're pushing it up to NAC. Is that what you mean, Ali, or should I go through more detail of the process?
What I meant, maybe I'll supplement that by saying that sort of so clinical cores were the main interaction with the subjects are sort of that are enrolled in the study. Well, we have outreach core as well that sort of is perhaps helping sort of the recruitment. But then during the evaluations, clinical core interacts with subjects who are enrolled in the study, and the data from them gets passed into this central database that Tung was talking about. And for the duration that they're basically in the study. And then the neuropath core basically for subjects who get to the point of either sort of donating the brains to the study or post-mortem sort of neuropathology information that gets collected. So that's the other end, basically. And the whole idea is that sort of we're trying to synchronize the data from the beginning to the end for each subject and make sure that sort of data is collected properly and sort of connected. So all the data that you're seeing here, Tung's talking about, for each subject is connectable through a unified subject ID. That sort of once you have a subject ID, you could go back and forth between different databases and sort of when you're searching, be able to access these different databases. But also the same sort of subject ID is used to connect the data in order to pass it to NAC, to the National Alzheimer's Association Center database. So that's the very rough overview of how these different parts of UW ADRC work together and sort of what this database is trying to achieve, this central database is trying to achieve it in terms of connecting them with each other.
Great. Thanks, Ali, for clearing that
Sure.
up. Yeah, totally. Anyway, I've worked so much with this that totally, it seems obvious to me, but obviously it's not obvious to everyone. Yeah, so what Ali is mentioning is this, 5 years ago, we created a UW Central ID, and this is the linker ID that matches up the data from all the various sources. So that if somebody went from clinical core to neuropath, they could have different, neuropath ID, clinical ID, but they would have the same single UW CID. Okay, so let's run through a quick use case here using the central database web interface. I'll just start. So I had a recent request for data that involved blood samples at the stored here at Harborview. Obviously, that's gone through clinical cohort, had a blood drawn. So to get that data, I would go through the query page. So this is available, and if anyone need access to this data, they can email Annika, and she'll provide.
Anyone who's with the ADRC UW or affiliated with the UW ADRC. We're not doing it publicly.
Yes, that's correct. You can't access this publicly. But yes.
So you have, if you're affiliated in any way with the ADRC, and especially if you have, do you need the net ID? Okay.
Yes, you do need a net ID to log in.
Yeah. I can help get a net ID for the people who may not be already at the UW. But again, if I know who you are, I can probably give you at least guest access.
Great, thanks. Okay, so these are going to be UDS subjects with blood samples stored at HMC. So this is basically the data stored here are tags. So as we pull in data from various sources, there's an engine that tags them. So whether they come from UDS, they get tagged, the subjects, the UDS subjects, or, the gender gets tagged as such. And then this is a query of those tags. So you can sort and filter based on this query. So we're going to query by the UDS subjects that gone through clinical core, stored at HMC. And what we want is blood and CSF tissue. So hit the little search button.
Sorry, Tom, as you explain things, maybe just mention what these acronyms are, because not everyone might know the acronyms.
Okay.
Thank you.
So the UDS's data it's a yearly survey it's a study, right, of subjects that have gone through clinical core in the ADRC. It's a longitudinal study of subjects possibly going to memory, issues, and eventually probably Alzheimer. The other acronym is, obviously, clinical core is Heart Review Medical Center. This is stored there. CSF, this is the lumbar puncture. This is the cerebral fluid from the spine. From this, you can look for tau and other biomarker. So we found 293 subjects that fit that criteria. So they have blood and CSF at Heart Review and gone to clinical core. Go ahead, Annika.
I just want to say, I put something in the chat. If anyone has any questions or wants clarifications or wants to schedule a meeting with me to go over any of these in more depth, I would be really happy to do that. So I have my email in the chat, and just email me if you want more information or more details or more personal guided tour of what's going on with the samples and data here at the ADRC. So.
Thanks, Annika. Okay, so these are the 293 subjects, and this is basically the results of the query search. The first thing we would get is their Shojaie ID. So these are the PT ID that come from the clinical core, and obviously we have a NAC ID associated. Some of them may have a bird ID. So these are subjects that have gone to the VA and have come to the clinical core here at Heart Review. This we can get some demographic data. So this is not all the data. This is just a select group data that we think may be useful for just a cursory, analysis. Finally, what we want to look at is the sample. So here are all the samples that are stored for these subjects. So we sorted by Heart Review. We can see that some of them are stored by neuropath, and if we go a little bit further down, thick red, and eventually Heart Review. And this is going to be saved off Excel. So the idea is that we can get you 90% of the data that you need, but that you want to sort it by just HMP, you would export this to Excel and just remove all the other ones, and that would leave you with just the Heart Review blood sample. Okay, so the second part of this is if you wanted to know the diagnosis for these subjects, right? So you have the blood sample, we want to know the diagnosis. So when it's query, this 296 subjects is saved to a scratch table in the database. So if we go to the UDS trait report, we can actually do report based on those 296 that we found. So for diagnosis, that will be under UDS D form. So I can just select on UDS form D and search for the diagnosis for the 296 subjects. So this is the diagnosis form for those subjects. Every single visit is accounted for each of the subjects we found. So for the first subject, they had 17 visits. And we go down to the diagnosis. I think it is right here. So 1, I think, is a control. So anybody have any questions on this, or any detail you want me to go through? But that's just
so clearly. I mean, I just preface sort of before opening up for questions. Clearly, there's a lot of information that you would need to have in order to be able to use this database. It's not something that sort of someone who's not familiar with the system would be able to automatically use it. It's not intended for that. As Annika mentioned, it's for people who are connected with the UW ADRC, and so you need some additional information for these to make sense. But we're here to help as a center. That sort of, if you have questions, we could help sort of with different parts of your investigation. Maybe I'll put this in chat that we have a general email in addition to Annika's email that sort of she put in chat. I'll put sort of the DMS help email in chat as well. That sort of this is your way of getting in touch with us if you have questions. about access to data or about sort of other things, you could send an email to dmshelp@UW, and that way we could provide help in a more systematic way.
Yes, and I'm available for training. I do this yearly training session where I will go through how to use a central database to query for data and look for data.
But now we're also happy to take questions if you have any questions right now, or we could push them to the end of the DMS session. No questions for now? So maybe if you stop sharing, I'll share my screen. Where am I? Okay, so for this second part, I want to talk a little bit about sort of, you saw all that data, right? I mean, you saw that sort of you have tons of data that you could get, and so that's not the only data that you could get. What do we do with it? And first of all, sort of, even before thinking of what do we do with it, which data do we use? I mean, how do we decide what part of this data to use? So I want to talk, I mean, and this is obviously not going to be enough. It's just a very, very broad overview of what you need to think about when you think about sort of your analysis plan and your data analysis. So please stop me if you have questions. I have probably more slides than I should, but that's okay. Please stop me if you have questions. So here's sort of the agenda, and in terms of some of the questions that we should think about as we think about sort of analysis of really any sort of health data, but more so also analysis of sort of data from ADRC, UW ADRC. So the first thing that you need to think about is sort of the goals of your analysis. And often that's connected to some hypothesis that you want to test. Not always, that's why I say often, because we could also do exploratory analysis. So sometimes we just want to examine data patterns and generate hypotheses, and this is especially in hypothesis generation is in early stages of study. It's sort of ad hoc. It's understood that this is the goal of it is to find something interesting that we would go and investigate further. Or we could be at the stage that we already have that knowledge. We already have a hypothesis, and we want to use that prior knowledge to do an explanatory analysis that is sort of based on a set hypothesis. And we'll talk about sort of details of these as we go forward. What type of results are you planning to have? What are types of data that are available, and how should you use those data? So what are the data that would help you answer the questions that you have? So you start with a scientific question, and then you think about sort of what are the data that would help you answer that question? And obviously throughout, you also need to think about sort of what is new about your study, about your hypothesis, about your analysis, and what are you going to get out of it? What are the deliverables? So I'll try to touch on these throughout, hopefully. Okay, so here broadly sources of data. You could have, and especially sort of human subject and health data, you could have records. These are data that are collected often for other purposes. So electronic medical records is a perfect example, or claims record, insurance claims record is a perfect example. But these are not recorded for the purpose of your study or your research. These are data that have been collected, but you might be able to use them. And there's a lot of interest these days in using electronic medical records or sort of insurance claims, but those data come with a lot of headaches as well. So data that we have at UW ADRC, at least some of the data from VA could be connected to some of these records, but the data that's sort of the core data is not records data, although sort of for the purpose of your study, it might not be exactly data that addresses your questions, but at least something that has been collected for the purpose of research. There's observational data, these are data that are collected for a specific research purpose. That's pretty much the type of data that we have at UW ADRC. These could be cohort data, case control data, cross-sectional data. We have a cohort at UW ADRC that's we've been longitudinally monitoring for a number of years. And then sort of each subject from the point that they're enrolled, they're often in the study till they're deceased, although sort of some people leave the study in between and for various reasons. So there's some complication with the data, but nonetheless, it's a cohort study. You could have survey data. These are usually passive data collections that may or may not include sort of specific individuals. So it could be surveys that are collected at regional levels. So for example, for zip codes, that then you would assume that sort of people in that zip code have the same environment, broadly speaking, that sort of you could use that data. So it's possible sometimes to link to these data. I haven't seen a lot of cases where we have used this type of data in UW ADRC research, although sort of there's been recent discussions with ACT in terms of trying to account for social demographic factors, and there you would need to use these survey data. There are interventions sometimes, and interventions are cases where the participants are assigned to a particular intervention. Perfect example of this that is close to our minds is COVID vaccine trials, that people were randomly assigned to receive the vaccine or not, and the different phases of this. Most commonly, it's like phase 2 where things become of interest. But it could also be that instead of individuals being randomized, the communities are being randomized. That sort of sometimes with vaccines, we randomize different communities to receive the vaccine or not, and sort of there are complications and reasons for doing that. And finally, there could be repositories, and of course we have repositories within our UW ADRC as well. These could be tissues, imaging, etc. And so these could be tied to records data, for example, to patient registry, or to observational data. In our case with our cohort, these are the repositories are connected to these observational studies. You could use these different types of data, but that depends on, again, so the type of study that you have and the questions that you want to answer, and what are the right data for answering those questions. One thing that you need to think about throughout is that the issue of whenever you're dealing with human subject data, there are ethical issues and sort of IRB approvals that you might need. One thing that sort of we have done is that the data that is available through the DMS central database does not have any patient identifiers. So any of that data you could use without sort of needing to worry about sort of dealing with additional approvals. But if you want to get beyond sort of data that is available at DMS, you would need to think about those and sort of get the right approval. So that's also a factor that you need to keep in mind. Okay, what type of analyses can you do? Again, broadly speaking, you could do descriptive analyses that sort of you basically just come up with summaries of your data. How your data arrange, what are sort of the characteristics of your data. This is not looking at a specific hypothesis, but just basically describing your data. On the other end of it, you could have very targeted questions. You could have causal inferential questions that sort of, you have a particular outcome that you're interested in, and I'll talk more about this, and you want to see what features could explain that outcome. Or you want to even go further in sort of mechanistic settings. Think about sort of given a change, for example, given that you're giving patients a particular treatment, how their outcome is going to change. How likely is it that sort of they would get severe COVID? And this is often in clinical trials that when we think about sort of mechanistic inferences. So these are two extremes. On the one end, it's like descriptive, we're just summarizing things. On the other end is like, this is a very targeted intervention. We want to see what the effect of that intervention is. And then in between, there's all sorts of predictive analyses that we might do. That's where we have some data, that's where we want to see what is the outcome, how much sort of we could predict the outcome based on some features that we have. And these could be prescriptive, that's where you have given data and sort of you want to think about sort of the choices that you want to make, and or diagnostics, especially in the case of biomarkers. Whether we could find, for example, a biomarker for detecting Alzheimer early, Alzheimer's disease early, and that's something that is of interest, obviously, to Alzheimer's disease research broadly, but also to some of the work that we do. Now, let's talk about each one of these a little bit. So this is descriptive analysis. And so a lot of people, when they think about descriptive analysis, they think about pie charts, which are not really the most useful visual tools, but this is an example of a pie chart that is accurate, unlike some of the others. The idea is that sort of usually your papers have a table one. And this table one is basically a summary of your data, different variables that you have. You could have continuous variables in that table, you can have categorical variables. Usually for continuous variables, we want to give a sense of the overall population of the distribution of that variable. We usually start with the mean or median, the center of that distribution, some measure of variability, that could be standard deviation or it could be sort of the range, depending on sort of what the distribution looks like. For categorical variables, the ones that are fit into multiple categories, again, you want to give a sense of clinically relevant distributions. What is the balance between males and females? What is the balance between sort of different categories of your variables that you have? So you report those. Sometimes in that table one, you stratify by values of other features. Often, so the categorical variables are used to stratify the distributions of those other variables. And that gives a sense of the population differences once you stratify to specific subpopulations. So that table one is usually something that most papers have it. It's a general sense of what your data is, what is included in your data. One thing that you need to keep in mind is that table explains the data in your study. And that, to some extent, would determine how generalizable your analysis results are to the broader population. And this is a really critical and important issue because, for example, when you're using data from UW ADRC, the samples are from Pacific Northwest, broadly speaking, but more specifically Seattle area, right? Greater Seattle area. That demographic is very different than patients who live in other parts of the country or other parts of the world. So you can't generalize your findings from what you find in this particular population to other populations. And that's to some extent the reason that's where you provide this table, because by looking at it, you would be able to compare your population to other populations and how generalizable that is. Key issue to think about in terms of how you could interpret your results. Then you could use different graphs and figures in addition to that sort of one table or some other tables. The general goal of graphs and figures is to provide something that is visually better understood than a table. So patterns are often well captured by graphs in a much better way than tables are. You could think about sort of when you're coming up with graphs and figures, what is it that sort of your figure is communicating? It should be a visual aid and sort of a way to communicate your findings or communicate your data. So it's important to communicate those without distorting the data or the findings. You want to usually minimize the visual complexity, but maximize the data to white space ratio. So you don't want to have a lot of white space in your figure, obviously, because that's a waste of your space. You want to use it to represent your data or findings, but in a way that is easy to understand. Don't make it too complex. And be careful about sort of some of the caveats that could make it a bit more difficult to understand figures. This is by itself is like almost a course, how to visualize data. I'll talk about sort of one resource potentially if you're interested. So I'm not going to have time to talk a lot about sort of data visualization here, but just some pointers and things to think about. You could also think about descriptive analysis for findings of your study. So for example, when you think about diagnostic biomarkers, you want to summarize the performance of your biomarker. You want to think about sort of the accuracy of that biomarker in some test data, how valid it is against gold standards. And a lot of times one common tool that is used is sort of ROC curve, that stands for receiver operating characteristic chart, but that comes from signal processing and not relevant for biomedical studies, but it's a very useful tool that basically on the y-axis you have the true positive rate, on the x-axis you have the false positive rate, and if you have a classifier that is basically just randomly guessing whether sort of it's a case or control, then you would have a 45-degree line, and then the higher that line goes towards the top, which is a perfect classifier, a better classifier you have, and the lower that line goes, a worse classifier you would have. So this simple chart basically summarizes the performance of your classifier for a range of decisions, because a classifier is not just a single decision, but usually, depending on the cutoff that you use, gives you a range of decisions. So it's an example of a visual summary of a model of a classifier, but there are obviously many more that you could use. Okay, so let's talk a little bit more about sort of inferential analysis. Now that we talked about descriptive analysis a little bit, let's think about sort of inferential analysis. And there are two different ways that sort of we can think about inferential analysis. One is in the context of associations, and that's the cartoon that I had on the first slide, that we know that sort of correlations and causations are not the same. So sometimes you just want to establish association, say that sort of this particular marker or this particular variable is associated with my outcome. Sometimes you want to go beyond that and think about sort of causation, or sort of drawing inferences that have that are potentially more helpful from perspective of treatment. The type of analysis that you use obviously depends on your outcome. More than anything, it depends on your outcome. What is it that sort of you're trying to compare? So if you have continuous variables, you could do various t-tests, a one sample t-test or a two sample t-test, depending on whether you have one sample or one population or two different populations. Or you could have a paired t-test where you have pairs of individuals and you basically want to compare the means of those. But that's very similar to the two sample t-test, but it's has better power because it's using the information from the pairs. You could also have like other types of tests for continuous variables. For example, one that is a lot of times used is the Wilcoxon signed rank test that sort of compares a feature to a general distribution. It could be a non-normal distribution. So it's more flexible than the t-test, which is more for like a normal distribution. You could also have categorical variables that sort of there's multiple tools for analyzing categorical variables. Chi-square tests are used a lot. Both chi-squared with goodness of fit test, but also chi-squared that compares two categorical features. You could do a Fisher's exact test instead of a chi-square test, which is the same as chi-squared, except that sort of it's more suitable for small counts. If you have small counts in your tables, in your contingency tables, and then the chi-square test is not potentially accurate, and you want to use the Fisher's exact test. There's another one that is called the Koskinen-Wallace test. When it's most appropriate when you have a categorical exposure and an ordinal outcome. This is a little bit out of order because I haven't talked about exposure and outcome yet as much, but in the setting when you have a categorical exposure, that sort of your exposure is like giving the vaccine or not, and then your outcome is ordinal. That sort of there's an order in the categories that you observe for the outcome, then the Koskinen-Wallace test could be used in that case. And there are various flavors of ANOVA that sort of basically test between and within group means and variability for categorical variables. And these are very similar to linear regression, so I'm not going to talk a lot about these. Of course, you guys are all sort of familiar with the concept of p-value, sort of what is a p-value. A lot of times, sort of a cutoff of 0.05 is used as sort of the gold standard for significant. That's somewhat arbitrary, but commonly used in practice. And then you could have p-values that are really small that sort of clearly indicate significance. You could have p-values that are borderline, sort of on either side of 0.05. And then you could have p-values that are larger than 0.05, which basically could be suggestive, but might not be significant. And so if you have that situation, it might be because A, you don't have enough samples to have enough powers to detect it, or B, there are other factors that you're not accounting for that potentially could change your p-value in either direction. Now, as I mentioned, so these ANOVA flavors are related to sort of the more general class of regressions when we use regression for studying association between two variables. And sort of a perfect example of sort of thinking about association is a scatter plot when you think about sort of the association between a quantitative variable with another one. So X and Y. And in that case, you often use a linear regression. On the last slide, I'll have a teaser about sort of why linear versus nonlinear. You could have a categorical outcome, then you would do a logistic regression. You could have an ordinal outcome, you do a Poisson regression. It really depends on sort of what the type of outcome is. If you have a time to event data, so you have survival outcome, you do a Cox proportional hazards model, or sort of other approaches. Or if you have outcome that is observed over time, it's longitudinal, which is the case a lot of times for the type of research that we do at ADRC, then you have to take that into account. And there are different tools for that. You could use a generalized estimating equation, or you could use a mixed effect model to capture the correlation between outcomes over time. So these are all sort of, by default, just give you a sense of associations. Now, you could also think about sort of fancier approaches for classification and regression. Broadly speaking, for classification, when you have a categorical outcome, you want to see how much your predictors or covariates or features, all these names are the same, would be able to give you information about sort of the likelihood of your outcome for each category. And so you could fit various classification models. These are like classical approaches from logistic regression all the way to sort of fancy methods that sort of these days are used more, decision trees and random forests and neural networks and sort of artificial intelligence and sort of supervised learning in general. So those are some of the approaches that one could use. The key here when you think about sort of classification and or regression in fact is to note that what you want to do is to make sure that you evaluate the performance of your classifiers on a separate data set compared to the one that you have used to build your classifier. This is really important. Very simple rule, surprisingly gets violated in a lot of papers that even get published these days. That sort of people somehow, there's a lurking of the information that they've used for training the model, so that's the building of the model, into the information that they use for testing the model. So that's a really important principle, and I'll sort of talk more about another resource for these types of analyses in case that's something that you're interested in. You could also have unsupervised learning. So these were examples of supervised learning. You could also have unsupervised learning, these are the cases where basically you don't have an outcome. So you just want to find patterns in your data. And you could think of clustering or dimension reduction. These are all sort of approaches that one could use for finding patterns. I won't have time to go into details, but in case you're interested in any of this, we have a bunch of summer courses at UW that either online, so it's at UW, but so they're basically offered virtually. Each one of them is 2.5 days, and there's 4 of them right now. We're thinking about sort of the 5th one. The 4 courses, one covers the basics of data wrangling. The second one covers data visualization. The third one covers supervised learning. And the fourth one covers unsupervised learning. For 2024, we might have a more advanced sort of machine learning AI module as well, but that one's in the works. Okay, so I'm almost out of time, but I want to talk a little bit about sort of how do you choose your analysis plan? And I want to get to the core of this, that sort of, what is your hypothesis? Think about sort of, what is it that sort of you want to investigate? And what is the structure of the data that would help you answer that question? Knowing those should sort of get you pretty far along in terms of thinking about sort of what is the right analysis. Once you know the question and the data, as I discussed, sort of the type of outcome determines the type of regression that you use. But that also depends on the question that you have. So once you know those, pretty much you know what analysis is appropriate. But then there are some minor questions that you might have, and sort of you're more than welcome to reach out to us. What I really want to advocate for here is that it's much more efficient for you and for us if you reach out to us in advance before you collect your data, before you go to the step of thinking about sort of what is the right data for your study, or that sort of if you're carrying out an investigation yourself. Come talk to us, because that you oftentimes might be able to give you some pointers that would help you in data collection to make your study better powered, or more targeted to answering the question that you have. I don't know, Jeff, how much time I have. I mean, I started 5 minutes late, so can I go for 5 more minutes?
Yeah, go ahead.
Okay, so I want to talk about sort of, in a figure, talk about sort of this really core idea. And I think hopefully this helps you think about sort of what is the type of data and what is the type of analysis that you need. So oftentimes we start with something that is of interest, some outcome. I'm going to call that Y. And usually when we want to think about sort of analysis and data, we have to think about sort of what are the potential causal pathways for that outcome. Even if we're doing an observational study and think about associations, it's always helpful to think about sort of what is the scientific knowledge that we could incorporate into our analysis. So if I'm starting with some sort of outcome, then I might want to investigate the association between some sort of exposure, which I'm calling X, with my outcome. So really my goal is to see whether I could establish association between X and Y. And ideally, I want to establish that sort of X causes Y, or that sort of changes in X are related to changes in Y. But that's complicated. So I might not be able to do that. But nonetheless, I have to think about the possible causal pathways. For example, because if I have another variable that could impact both X and Y, and I don't account for that variable, this is a confounder, Z here is a confounder, then I would automatically assume that sort of X is associated with Y, whereas the association is actually the result of this confounder that changes both X and Y. And there are many examples, fun examples of this that I'm not going to have time to go through. On the other hand, there could be other types of variables. There could be variables that are caused by both X and Y, that are downstream of X and Y in terms of causal pathway. And in that case, if you do adjust for something like C, these are called colliders in sort of causal inference language. But if you adjust for C, then you incorrectly, again, conclude that sort of X is associated with Y, even though X might not have any association with Y. So it's really complicated. On the one hand, you want to adjust for confounders for Z. On the other hand, you should not adjust for colliders, C. So it's really important to think about sort of what are the right variables to include, because that would inform you which data you need for answering your scientific question. So it's not just about sort of the association between X and Y and go collect X and Y. You also need to think about sort of what are the other factors that you need to account for as you're investigating the association between X and Y. And of course, the challenge a lot of times when we think the reason that this might not be able to establish causal relations is that, and unless we have a clinical trial or unless we have randomization, is that there are other variables, other confounders that are unmeasured. I'm calling them U, which we don't get to collect in our data. We don't have them. And because we don't have them, no matter what we do, we might not be able to explain away the effect of these unmeasured confounders. There are some thoughts about that and some strategies. That's something I'm interested in. I'm happy to talk with you about it if you get to that point, but just keep that in mind, that you might not be able to get to that point of thinking about sort of causal relationships. And there are few other types of variables too, which I'm going to skip over because I'm already out of time. Okay, so some advice for choosing an analysis plan: really keep it simple. Fancy methods could be helpful down the road, but at least your initial analysis should be as simple as possible, because if it's about the science, it's about the scientific relations between variables, not if you're able to establish something with a fancy method, but you can't establish it with a, or at least you can't get a sense of it with a simple method, then there's something probably off in terms of your scientific approach. Look at sort of similar papers in the papers that in the journals that you're targeting to see what analyses they use, and think about sort of who's the audience for your analysis and what are the approaches that are helpful. Okay, it's usually good to do some sanity checks. I'm going to skip over this because I'm out of time. Again, so the point is that things are complicated. There are multiple pathways that could be between your X and Y that sort of could explain the association between X and Y. And you have to think about those. So I won't spend too much time on this. And I'll just end it here with some like a teaser on sort of different types of analyses you could do, and sort of some jokes about sort of what messages they send.